Imagine you hand the cashier a $10 bill, then sprint next door and hand the same bill to a bookstore. In the physical world, that's impossible. You can't be in two places at once, but digital money is just data, and data can be copied. Bitcoin needs a mechanism that makes digital payments impossible to use twice. That mechanism has two parts: precise references called outpoints, and a live ledger called the UTXO database. To understand how, let's look inside a Bitcoin transaction input. Every transaction has one or more inputs. The input count is encoded using a compactSize integer, Bitcoin's variable length encoding for whole numbers. If the value is between 0 and 252, it fits in 1 byte, no prefix needed. For values up to 65,535, a prefix byte 0xFD signals 2 more bytes of data, 3 bytes total. Prefix 0xFE means 4 data bytes, 5 total. Prefix 0xFF means 8 data bytes, 9 total. Most transactions have fewer than 253 inputs, so a single byte handles the count. Now that we know how many inputs there are, let's look at what each input contains. The first and most important field is the outpoint. An outpoint is a pointer, not the coins themselves. An input holds no value on its own. It references a previous output where value was assigned. The outpoint has two components: a 32-byte transaction ID called a txid and a 4-byte output index. The txid identifies the previous transaction. The output index selects which specific output within that transaction. Together, these 36 bytes point to exactly one previous output on the entire blockchain. Let's trace this with a real example. Alice broadcasts a transaction in block 774,958. Her input's outpoint contains a txid pointing to an earlier transaction where Alice received coins. The output index is 0, the first output of that earlier transaction, holding 100,000 satoshis, and that's the money Alice is now spending. The full node has found the previous output Alice referenced. It extracts 4 critical pieces of information. First, the amount, 100,000 satoshis. This tells the node how much value is being moved. Second, the authorization conditions, the spending rules embedded in the output script. These define what proof Alice must provide to spend these coins. Third, the block height and the median time passed of the block containing the output. The node needs these values for time lock checks, rules that can prevent spending before a certain time or block height. Fourth, and most important, the node checks whether this output still exists in the UTXO database. UTXO stands for Unspent Transaction Output, the set of all outputs that haven't been spent yet. If the output has already been spent, it won't be in the database and the node rejects the transaction. Now Alice tries to cheat. She creates 2 transactions. Transaction 1 pays Bob 90,000 satoshis. Transaction 2 pays Carol 90,000 satoshis. Both inputs reference the same outpoint. Both point to Alice's single previous output of 100,000 satoshis. These are conflicting transactions. 2 or more transactions that attempt to spend the same output. Alice is trying to spend the same coins twice. This is the double spend problem, the fundamental threat to any digital currency. Here's how Bitcoin stops it. When a node receives Alice's first transaction, it tracks the reference output as pending. When the second transaction arrives referencing that same output, the node detects the conflict and rejects it immediately. Only one of these conflicting transactions can ever be confirmed in a block. The UTXO database is the enforcement layer. Every full node maintains its own independent copy. When a new block arrives, 2 things happen. For every input in the block's transactions, the node removes the reference output from the UTXO database. Those coins are now spent. For every new output created by the block's transactions, the node adds it to the database, new spendable coins. After processing, any future transaction referencing an already spent output fails validation. The output simply no longer exists in the database. A common misconception is that miners prevent double spending. In reality, every full node enforces this rule independently. If a miner includes a double spend in a block, every other node rejects the entire block as invalid. There's one more gotcha that trips up even experienced developers. Transaction IDs have a byte order problem. When a txid is stored inside a serialized transaction, the bytes are in little endian order. That means the least significant byte comes first. But block explorers, APIs, and the Bitcoin Core's command line display txids in big endian order, with the bytes completely reversed. Here's what this looks like in practice. On the left, we have the internal representation, little endian. A developer extracts txid bytes from an outpoint in raw transaction data. The bytes start with A1, B2, C3, D4, E5, F6, A7, B8, and so on. They paste this directly into Bitcoin client get raw transaction. The result? An error, no such mempool or blockchain transaction. The txid looks perfectly valid, but the lookup fails. Now on the right, we have the display representation, big endian. The fix is to reverse the entire byte sequence across all 32 bytes. So A1, B2, C3, D4, E5, F6, A7, B8 becomes B8, A7, F6, E5, D4, C3, B2, A1. Paste the big endian version into the same command, and the transaction is found successfully. Between these two panels, you can see the byte flip transformation. Each byte swaps position, reversing from one end to the other. This mismatch is an artifact from Bitcoin's earliest code, and it's now permanent. Every developer working with raw transactions must reverse txid bytes when moving between serialized data and display tools. Let's put it all together. Outpoints give Bitcoin surgical precision. Every transaction input uses a 32-byte transaction ID plus a 4-byte output index to reference exactly one previous output. No ambiguity. The UTXO database gives full nodes a fast, reliable way to verify whether that output is still available to spend. Spent outputs are removed when blocks confirm. New outputs are added. Any attempt to reference a spent output is rejected. Together, Outpoints and the UTXO database enforce Bitcoin's most critical rule. You cannot spend the same coins twice. You don't need to trust Alice. Every node independently verifies every claim. The authorization conditions, how Alice proves she's allowed to spend, are handled by input scripts and witness data, topics for upcoming episodes. Bitcoin doesn't prevent copying data, it prevents copying value, and the Outpoint UTXO system is how.